Hello, everyone. So, in this part two class, we'll be looking at the basic feedback system of an automatic control system. For a system to be said to be a control system, that system have to be a system that has a feedback. It has to be a closed loop system. So, that is when you can have, you know, a feedback in that system. So, the basic feedback system that has one feed forward loop and one feedback loop. So I wrote here, I said one of the crucial ingredients of automatic control is feedback. Without feedback, you can't have automatic control. And that feedback provides mechanism for authenticating the effects of parameter variations, and disturbances, and enhancing dynamic tracking ability. What are we saying here? We're saying that without the feedback on the system, there's no way we can see the effects of various uh, parameters, the variations in those parameters on the output of that system, or the disturbance, external disturbance on that system, or any way by which we are enhancing the dynamic tracking ability of that system. In real life approach, for instance, if we have an air conditioning system whereby the room that is being cooled with that air conditioning system has a temperature sensor that measures the temperature of that room as against the set point of the air conditioning system. Once the set point in the room is already attained, then what should happen is that the air conditioning system should stop cooling the room. That automatic control can only be made possible if there's a feedback between what the sensor is measuring as the temperature in that room against what the AC system is doing. So that is when you have a feedback system. Now, when we're talking about a basic feedback system, we're saying that that system has a single forward loop and a single feedback loop. So here, like always, R is the input, Y here is the output, and whatever is measuring the value of the output, this is a pick-off point here. Whatever is measuring the value of the output is this H into D, which is the feedback. And this is a sum block here. So the difference between the output here and the input of R is this error of E that we have here. So whatever this error is, what a control system wants to do is to ensure that the value of E here is minimized. So whatever value that E is, the system must be able to compensate for that difference, either to convert it into a voltage that will go again into the system itself to ensure that the output here and the input here, the difference here is as close to zero as possible. That is what we mean by dynamic tracking ability of that system. So for the system to dynamically track the desired output as against the input, and that is what we're going to be looking at, using all the manipulation we talked about to make a more complex block into a basic feedback system form, where the system will only have one forward loop and one feedback loop. But looking at this figure 2.3.9, we can write the transfer function of this very BFS, your basic feedback system, because we know that a transfer function TF is ratio of outputs, which in this case is my Y also with respect to time, because we are dealing with continuous systems, and R with respect to time in this case. So, but if we look at the mathematical model of this BFS, we have variable E, we have Y, and we have R. You understand? So uh, E here equals, E here is Y, Y minus whatever the value of R is, because what has happened for us to have E. Okay, let me just do this first. So Y, which is the output, in this case, Y, which is the output here, Y equals R minus E. Y equals R minus E. So E also runs into this block. So that will be E into H, sorry, E into D, E into G, E into GD, E into GD, because E runs into this. To get that value. But let me not complicate the maths so that we just get an understanding of it. So Y is the signal here. This is a pick-off point. The same Y flows into this, right? And flows into this negative terminal. Flows into this negative terminal here. So R minus Y into this gives E. So E, which is the signal on this line here, is as a result of Y, the same Y from this pick-off point runs into here. So that will be R minus Y H D in brackets gives E. So that will be Y, capital Y here, into H into D. So that is what is giving us E in this case. But Y itself is a result of E GD equals Y. So Y equals E G into D. So that is what is giving us Y. So let's call this equation 1. Call this equation 2. So we know our Y is our output, our E, our R is our input. So if we put equation 2 into equation 1, so just substitute our Y as this. So we are going to be having E. This is equation 1 into R so let's just put in our equation 1 into equation 2. So we have Y equals E this, and we know that E is all of this. So Y equals R minus Y H D dot G dot G. Let me just rub this so that it will be clear. Dot G into D in brackets. Because what has happened here is that this Y equals E G D into brackets. We already know that this is E. So we brought all of this as E, which is this dot this. So we know that for us to have a transfer function, it is Y over R, which is output over input. And all our output will come to the right side of the equality sign, while our input should remain on the left side of the equality sign. So R is our input. We'll leave R on the left, while our Y would go to the right side of the equality sign. So we'll be having here y equals, this GD will multiply the whole variables here. So that will be R G D, minus y, because this GD is multiplying everything here, because we are replacing E here with all of these values. So this GD is multiplying everything here. So that will be y HD D in brackets, dot again GD in this case. So let's bring our y to the right and our R, which is the input, to the left. So that will be y plus y HD, y into HD dot G into H into D in this case. And we have R G GD here. So we can factorize it and say y into 1 plus HD GD equals R G GD. Equals GD. So transfer function is output over input. So if we bring cross multiply, we're going to have y over R equals GD divided by 1 plus HD GD GD. So here is the transfer function of this BFS. This is transfer function where we have our R, your output over input. So if you look at the node also, you see that that's what you have here. So the function gd.hd, which is what we have here, represent the transfer function around the loop of the feedback system, and it's called the loop transfer function. That's your LTH. So your gd.hd is called your LTH. This is what you have here. gd is called your loop transfer function, and the for loop transfer function is your gd. This is what you have here, your gd for loop transfer function. So your 1 plus gd.hd, this is what you have here, 1 plus hdgd, still the same. Is what is now your denominator. So that is 1 plus your transfer loop, your loop transfer function, sorry. So this is the transfer function. So let's just look at some examples to see how these things actually work in operation. Let me rub this part of this whiteboard. And just rub that part and change my pen. So this is an example. You have nested feedback loops in majority of block diagram. So you have pick-off points, you have a lot of blocks there. So the example that I'll be showing here is an example of a mass spring damper model. This is the mass spring damper model. This is what you are going to be having as your question. You understand? So I've completed the solution here. But from the question here, the question is to convert this block into a basic feedback system. And we know that for a basic feedback system, there has to be just one forward loop and one feedback loop. Looking at this spring mass damper model, we can see that we have two feedback loops. This is one, this is another one. So we need to find a way to reduce this block such a way that we have just one forward loop and one feedback loop. You understand? So, we already talked about series blocks reduction, parallel block reduction. We have also talked about moving a pick-off point, upstream or downstream, and also moving a block, over a summing junction, either upstream or downstream. So that is what we are going to be using to reduce this block into a basic feedback system equivalent. So the first thing we are going to be doing here, is to look at this very diagram. Where can we use series reduction? Where can we use parallel reduction? Where can we do movements of a pick-off point, either upstream or downstream? Where can we move a block over a summation junction, either upstream or downstream? And if we are looking at this, we can see here that this 1 over m and 1 over d, these two, they are in series. Why are they in series? Because a signal comes into 1 over m, the output of 1 over m goes into 1 over d. So that makes these two blocks, in series. And also the output of 1 over d goes into 1 over d here. That makes these 1, 2, 3 blocks in series. But we can't take them as this multiplied by this just yet because of this pick-off point in between this block and this block. So the first thing we're going to be doing is to move this pick-off point, move it downstream. When we move a pick-off point over to the right of a block, we'll move it downstream. And the inverse of the block we moved it over will be on the feedback part. What I'm just saying is what we have discussed before. Moving pick-off points downstream. When we move downstream, move this over B downstream. The inverse of the block we move this pick-off point over will appear on the feedback part of that pick-off point. So when we move this over B, 1 over B appeared here. So that's just what we are going to be doing here. In this case, we have 1 over D. So when we moved over 1 over D, what we are going to be having is D, because the inverse of 1 over D is D. That's why we have D here. You understand? So having done this 3 now becomes series. This output goes into this. The output here goes into here. So this now becomes series. And we can multiply them together into a single block. So if you multiply 1 over m times 1 over d times 1 over d, we're going to be having 1 over m d squared. So this is what we have here, 1 over m d squared. You understand? Now, we also have here 2 blocks in series because the output from d here flows into b. So we can multiply this together and have bd. So when we have bd now becomes parallel to this. Why? Because the same signal flows into this line of the block and also this line of the block, because the same output here is being picked off from here and another pick-off point is here. The same signal that is flowing here, same one that is flowing here. So based on that, these two blocks are in parallel. So multiply this by this to series BD. So BD is now in parallel with K. So when they're in parallel, you add them. So that will be BD plus K. And that's why we have BD plus K here. So doing that, we are able to do the reduction of this block from this complex block into a BFS using the block manipulation that we talked about. And that is the explanation I'm trying to give here. If you go through this explanation and what I did, you will see that it's just the same. So let me just run over this block again. This is the question. We are told to reduce this block into a BFS. And I can see here I have this and this in parallel. However, I can't consider them straight. Why? Because I have these pickup points in between. So I move this pickup point downstream over this 1 over D block downstream to the right. And once I move the pickup point over a block downstream, the inverse of that block will appear on the feedback part, which implies when I move this pickup point here, the inverse of 1 over D, which will be D, will appear on this part, which is what we have here. That's why we have D here. So from there, we have these three as series. And when they are in series, I can multiply them. So 1 over M times 1 over D times 1 over D. So that will be 1 over M times 1 over D squared, which is what we have here. These two now are in parallel, are in series. BD, multiply them together, that's BD. Now, because the same signal that is flowing in this channel is what is flowing here, because this channel is picked up from this channel. This channel is picked up from this channel. So BD now is in parallel with K. And when they're in parallel, I can just add them. So that will be BD plus K. So BD plus K. So I have a single feed forward and a single feedback. So that is turning in this complex block into a single, into a basic feedback system. So here is another one. We have this high performance control system here. We are told to reduce this same high performance control system from this complex outlook here into a BFS, having just one feed forward and one feedback loop. So the first thing is to understand the model here. That's the first thing. And look at it. Because here now, these two blocks, though they are vertically stacked, they are not in parallel, because the signal that is flowing into this C2S is R, while the one that is flowing into this C1S is the signal that is being picked up from here, which is Y. R minus Y is what is flowing into this one. So they are not in parallel, though they are stacked, but they are not in parallel. So I can't just take them as parallel. So what can I do here? I can move this block, downstream here. I can move it downstream and look at the model, because you here being the sorry, let me just change down my U. It's not looking like U. So U here, which is signal on this line, came from this R into C2S, R into C2S plus whatever is coming out here, which is Y, R minus Y, C1S. So plus R minus Y, in brackets, or let me just say C1S into R minus Y, whichever one I want to call it. So I'll just say C1S, into R minus Y. So that is U here. U here is R C2S comes here. Y is being picked up from this line. So Y comes to this point. So R minus Y comes out here, runs into C1S and comes out here. So that is the model just for this U. And all of that goes into GS to give Y. So Y itself is U, U dot GS, S in brackets. And we know that all of this is U. So all of this going into GS gives us Y. So if I now want to move this C1S over this junction here. So I move it here, you know, if I move it here, so what should this block look like to ensure that I have not changed the mathematical model? Am I going to have a repeat of this block on this line or something, when I move this block over this summing junction downstream to this point? Mind you, U is between whatever is coming here and GS. So let me just do a small sketch of that if I would. So I'm going to have R, this line. I have my sum junction plus minus here. So Y is still coming from this part. So now I have moved C1S over this sum junction. So I still have this C2S here, C2S on this line, and this one comes here, and I now have my C1S here, which I've moved over the sum junction. I have U in between that and GS here. GS here before I can now have Y as output here. And this is what is being. So if I move this C1S over this summing junction, which is what I've tried to sketch here, I'll check this model for you to see if it is correct or not. This is the initial model of U. Now I have moved this over this sum junction. So what that means is I'm going to be having at these points, what I will be having at these points will be RC2S, R minus Y comes here. So that will be R C2S, on this sum junction. R minus Y comes here. So plus R minus Y in brackets. So all of that will run into this C1S. So let me just put a large and say C1S. So when all of that run into C1S, they will now give U. So let's now compare the U here now, when I've moved this block, over this sum junction, and the original U here. So if you look at it, that means I'm going to have C1S, open this bracket. So that will be C1S times this, which is the same thing as this. But C1S times this will now be RC1S C2S, which is not what I have here. I only have RC2S here. So moving this over this summing junction will mean that this will multiply all of this. Now, the only way that this can be here on this summing junction, on this side of the summing junction, and still retain this model is if I already have on the signal line of C2S inverse of C1S. So I'll be having R C2S, divided by C1S plus R minus Y, R minus Y, sorry, let me just move back here. R minus Y C1S equals U. So this is the way that if I multiply this by this to give me C1 R minus Y, and if I multiply it by this RC2S over C1S, I will still have C2S, which is what I have initially here. Let me just minimize this so that I can see everything in one frame. So and pick my pen back. So what I'll do is that I'll now go to this line of C2S and add inverse of C1S there. So that will be C1S inverse on this line. So let me just say C1S inverse C2S. So that's the only way I can have this model that will still give me the same U as this that I have initially. So you see that that is what has been done. That has been done here. You understand? So from there now, I know that this and this are now, this C1S and this GS are now in series. I can multiply them together. And this now are also in series. I can multiply them together. So which is what has been done here. C2S, C1 inverse here, and C1S here, and GS here. But you'll now be wondering, so how did this one come here? So if you look at this very diagram, C1S inverse, C1S inverse dot C2S, that is what we have here. So if I factorize this too, so I just have C1S inverse dot this. So if I make my R the subject in this case, so let me just rework this part for you. Now, from the diagram, we know that these two now are in parallel. This C1S inverse, C2S inverse, they are in parallel. Now, these two summations, they are just about doing the same thing. We can decide to move this pickup point, this signal to this point, because R minus Y here, if we take it here, is equally R minus Y. So I can just erase this signal from here and just put it into this summation that I have here. So I will not be repeating that summation twice. So now I have, this is still minus. So Y is coming here as negative. R is going into this 2. So once we have moved this, remove the equality sign here, the summing junction here, I have moved this Y to this point. What we're going to be having is R into this and R here. So what we're going to be having is R into C1. Let me just drop this. Is R C1 inverse S, C2S plus R, then minus Y is coming here, minus Y. The variable here, let's call it Q. The output signal there, let's call it Q. So here I can just say, let me factorize R and say R here will be 1 plus C1 inverse S, C2S minus Y equals, this equals Q. So, and that is what you have here, R into this, all of this. So you still have your minus Y coming here, and the product of this, since they're in parallel, You now have this. So this is BFS of this system. Also, we have another one here saying this is a system that you are told to reduce into a BFS form. So if you look at it, so we look at the first thing here is that we have these two blocks. They're in parallel. Are they truly in parallel? They're in parallel because the same signal is flowing into them. The same signal that flows here is the one that flows here because this is a pickup point of this signal. So in that case, I can just take this as parallel. So this plus this. So let me just rub this side of my whiteboard so that you can see what will be done. So that will be 1 over S plus 10 because this is parallel. So that will be S1 plus 10. So the equivalent block will be 1 plus 10 over S for these two, right? Also, these two are in series. You know, they're in series. But before I can multiply them in series, I need to move this pickup point from here downstream so that the inverse of this will appear on this line. So if I move this here, S will appear on this line, So from there I can do this times this. Mind you, once we do the parallel of this, we don't need this summation sign again. So what we're going to be having will now be 1 plus 10 over S, as a block going directly into this 1 over S plus 5 plus 5, then since I moved this pickup point from here to here, so that will run into 1 over S. So I will now have these two pickup points here. So S will be on 1, the inverse of the block I moved it over. S will be here. This is 0.15. Be here, be here, and both of them will be running into this summing junction where I have R here, and I have these two coming as negative terminal here and going into this point. This is my summing junction, So from there, all of these three now becomes parallel. Sorry, it becomes series, and also this one becomes series. Mind you, this is my output Y. So I'll be having these two now, they are in series, so that will be 0.51 S. The equivalent of this 0.51 S, and also all of this, 1 over this times this times this. So that will be S squared into S plus 5. So I'll be having 1 plus 10 divided by S squared into S plus 5 as the only block that will be on this line. And this will be 0.15 S, on this line. So 0.15 S here. And since Y is on this feedback loop, for me to merge these two, that will now be Y plus 0.15 S, will be what will be on this single line if I merge these two as parallel together. So I can factorize my Y out because my Y is on this line here. So that will be 1 plus 0.15 S. So if we go to this, that's what we are having here. That's what we are having here. This, 0.15s plus 1. So if I factorize my y out, that'll be 1 plus 0.415s. So we have here as the feedback. Then also s squared s plus 5. S squared s plus 5. And mind you, when we're doing the multiplication here, we made an error. We should have here, when we're doing this, s will have multiplied 10. So that will be 10s in this place. 10s here. So that will be 10s plus 1, because when we did this, that will be 1 over s. That will be 1 over s plus 10. So s here, 1, 10s that have been here. So 1 plus 10s, s squared, s plus 5. These three signals in series. These two in series, then these two in parallel. So that's what we have here as the BFS of this very system. So let me just run over it. Initially, we have this, these two are in parallel, but for us to know they're in parallel, we need to check. The same signal is flowing into them, so they're in parallel. So 1 over s plus 10. So 1 over s plus 10. So that will be s as denominator, 1 plus 10s. So that's what we have here. So once we merge these two as parallel, we don't need this equality sign again, this summation sign again. So these two now runs directly into this. So this into this directly. And we have this already, which is this. So move this over this pick-off point over this summing junction. Once you do that, the inverse of this will appear on this return path. So with that, these three now can be treated as series. So all these three together as series. We have moved this over this summing junction. That's why s is showing up here. The inverse of this is showing up here. So these two now are in parallel, are in series, sorry. So that will be this times this. While all of this also in series, that will be this 3 times this times this times this. So this times this times this. So s times 1 over s, so that will be s squared times s plus 5. So that's what we have here. The numerator here also will just retain itself. So that will be 1 plus s 10s, which is this. So this time this will be 0.15s. This other signal line of y, which is parallel to it, so that will be y plus this. So if I factorize my y out, that will be 1 plus y into 1 plus 0.15s. And that's what you have here. So 0.15s plus 1, because this is y. Y is on this line, y is on this line. So 10 plus s plus 1, 10s plus 1 divided by s squared, s plus 5. So that is 1 plus 10s divided by s squared, s plus 5. So that is the BFS. This is the BFS of this system. So simulation, we already talked about that. Most visual simulation environments perform basic functions such as graphical editing, analysis, and simulation. Probably if you are using Simulink, you can do graphical editing on Simulink, you can do analysis on Simulink, you can do simulation on Simulink. Graphical editing is used to create, edit, or store and retrieve models, while analysis is used to obtain transfer function, compute frequency response, and evaluate sensitivities to disturbances, while simulation itself is the numerical solution of block diagram models. Simulation itself as a process entails 3 steps. You do your initialization, you do your iteration, and also the termination. Initialization is when you set up your blocks, you put in the values into them, you do your iteration, and termination is when you actually run your model to obtain your outcomes. Now, here I've listed some visual programming platforms. I talked about MATLAB Simulink from MathWorks, LabVIEW from National Instruments. You have your EZ5, your Boeing. You have your Visual Solutions, that's your VSIM. And you have your matrix system build from National Instruments as well. So these are other environments aside Simulink. I use Simulink, like I said earlier, and what I've used in the video previously is also Simulink. So in the next part, we're going to be looking at block diagram modeling, the direct method, and later we'll be looking at the indirect method of building a block diagram. So thank you very much for your time.